about another IPC problem, classical IPC problem, and this is an improvement to the dispatcher worker problem. So to get things started, what I'm going to do is copy the code. We'll say make dir dispatcher worker IPC. All right, and we're going to copy the code from the, let's see, the reader-writer's IPC. We're going to copy that to the dispatcher worker as a kind of a template. Okay, and then what we'll do is we'll kind of get things set up without using synchronization, and then we'll fix it. Whoops. Okay, let's try that again. I'm going to copy dispatcher worker IPC. We're going to, let's see, we're going to copy reader writer IPC to dispatcher worker IPC. There we go. CD to dispatcher worker IPC. Okay, excellent. All right. So let me explain the basic idea. We'll go to the main program and think about this. So the main program, we're going to make this our dispatcher. And we're going to imagine, just for the sake of simplicity, that the main program is receiving requests from somewhere. Now, earlier in the semester, when we were looking at interprocess communication, we actually had this idea of a dispatcher worker mechanism so that we could receive requests to look up prime numbers, and we could process those requests, and we could be open as the server to receiving multiple requests for prime numbers simultaneously. And we had limited the number of requests to 3, but there was no reason why it had to be limited to 3. It could be quite a large number. The approach that we had there was effective because, and worked just fine because the prime number server had already built up all the prime numbers, and so it was a read-only system. So we could have lots of threads reading from the prime number array, and we didn't really have to worry about synchronization in that case because we had concurrency, but we only had read with concurrency. You have to worry about synchronization and their race conditions specifically. Excuse me, when you are in a situation where you have multiple threads running and read-write access to some shared data. So for a more generalized version of the dispatcher worker problem, what you want to have is a dispatcher which is dispatching requests to worker threads. And those worker threads do some kind of work. All right, so let's just modify this so that we'll just start out with just a worker. And we don't have a database, and I don't know what we're going to do yet for some words. We're going to need them, but we don't need them right now. Okay, so here's our worker, and maybe we'll call it worker 0. All right, and worker 0 is a worker thread, and it's going to invoke the worker method. And we'll pass in 0 as the ID for the worker. That seems reasonable. Okay. And we'll just put a pthread join at the bottom here that's going to look for worker 0. All right, so far this is a real simple design, but that's okay. And we'll make this method right here that says writer here, we'll call this our worker. And there's our parameter, and we'll say int ID equals int star param, put that in parentheses, and star it. Now, I want to remind you why we do this kind of strangeness here, where we're passing in an integer reference from an integer that's created on the heap. And we are then typecasting that integer reference and then dereferencing the integer. Now, the reason why we're doing that is because if we try to pass in anything that was on the stack here, like let's say I created an int ID and I set it equal to 0, and then right here I passed in 0 instead of new int 0, that would be really bad. Or sorry, not 0, you can't do that. I passed in ampersand of ID. So the challenge with this is that I can end up in a race condition if I try to reuse ID here. Let's say I had a worker 1 that was passing in, calling worker, and just before that I said ID equals 1. All right, so the idea is I'm just trying to reuse this ID here. So the challenge with this particular technique is take a look at the race condition up here. The race condition is take the address that's passed in, dereference it, and copy it into ID. But if this create stalls and this create gets to run before this create, which is totally possible. There's nothing that says that worker 0 gets to start running before worker 1. It's just the two threads are created near simultaneously. So what could happen is this create stalls, ID gets reset equal to 1, this create runs, the ID, the address of ID gets passed in, and the ID for worker 1 is set to 1, but now we let pthread create for worker 0 start running, and the ID gets dereferenced again, and the ID for worker 0 also gets it equal to 1. So that's bad news. So to avoid that to keep that from happening, what we're going to do is we're going to do a new int 0 here. So we're guaranteed to pass in a fresh integer from the heap that's only going to be used by worker 0. Now the downside to that is that's a memory leak because we have to make sure that, I guess when the thread ends, we'd have to make sure that we deleted that integer. That's kind of a cool idea, so maybe I'll add that right at the bottom if the thread ever ended. I think it's going to. All right, delete param. Okay, so we get rid of our memory leak. All right, now, what is the worker going to do? Well, we're going to simulate it doing work, but it's not going to be in a while true. It's just going to do some work. So we'll say sleep random times 2. So there we go. We're going to sleep for a random amount of time. That's going to simulate work. All right, and so when we're done here, we're going to say pthread exit, indicating that we're done doing the work that we need to do for this worker. All right, so the main program is going to dispatch worker 0. Worker 0 is going to invoke the worker method, and it's going to do some work. Fantastic. So what's the problem? Why do we have to worry about race conditions and synchronization and stuff like that? Well, we want to place some limitations on how much work the dispatcher allows to happen, okay? So we'd only like to have, let's say, upwards of about 100 workers running at a time. And once we have 100 workers running, we want to basically limit the dispatcher from running any more workers, okay? So now we have a problem, right? Because if I were to do this, let's set things up so that we can have a lot of workers, okay? So pthread worker 100. So now I've got an array of pthreads. We know that that ID thing isn't going to work. All right. Now, why don't I just run this for forever while true. All right, and so in this while true, what we're going to have is we're going to have the worker, a pthread create's going to get executed. So here's the pthread create. And we're going to pass in a worker. But which worker are we going to pass in? Well, I think we'll just have like a count, basically. Oh, I see what I did here. Okay, we're not going to use an array. So let me go back here. All right, so we're going to pthread create. We're going to create a worker thread right here. So pthread underscore t worker. We'll call it worker. Worker data equals star worker data equals new pthread underscore t. All right. And then we're going to do a pthread create with the worker, and maybe we'll just give it, and we'll have a count here. So we'll have our count. Worker count. Yeah, we'll just call it ID count. Okay. And we're going to pass in an integer which represents ID count. We'll just use this for debugging purposes. And then we'll add one to ID count here. And let's see, what else do we need here? Oh, we got to pass in worker data. Okay. And there's one other little bit of weirdness here, which is we're going to do something called pthread underscore detach. Okay, and what that does is it allows us to have more than 254 pthreads available. All right. Now, if I were to let this run, let's just review it for a second here. So we've got kind of a generic way of creating, well, so it's weird that I did this dynamically created pthread on the heap, right? I could have, alternatively, I could have done this. I'll just comment that out for a second and write down pthread underscore t worker data. All right, and then done a pthread create with worker data. Now the problem with doing this though is as the while loop iterates, every time the while loop iterates, this local variable worker data would get removed from the stack, right? every time I go back to the top of the while loop, any local variables get removed from the stack. So that's not a good choice. What's better is if I create the memory for the pthread that I'm about to create, the metadata for the pthread, if I create that on the heap, that's not going to go away when we get back to the top of the while loop. I'm going to lose this connection, this worker data connection, but I'm not going to, I'm going to have a little bit of a memory leak. I think that's what I'm trying to say. But I'm not going to lose that metadata associated with pthread create, or with the, with pthread create. And then additionally, we have this pthread detach. So that's a special piece of code that gets run. If you do lots of pthread creates, there's kind of a limit that the operating system puts onto the number of threads that a process can create. So pthread detach says, don't worry about that limit. We can go bigger. All right, so this is, I could write a little bit of code here and just say we're going to get some work to do from somewhere, and then we're going to create a worker thread, and that worker thread will do the work. That's kind of the idea of the dispatcher worker design pattern. All right, and getting some work to do from somewhere could be something like we prompt the user and say, do you have some work for us? Or this could be embedded back in that dispatcher worker prime number server. So this could be some code that's waiting for a client to connect and provide it with a number. And we have to determine if the number is, the work that we have to do is determine if the number is prime or not. So that would be another example of getting some work to do from somewhere. So after we've gotten the work to do from somewhere, then we'll create the worker thread, and then the worker thread will execute and do the work for us. Now, I'm wondering if you see a problem with what I've got here. The problem is we could have an insane number of threads running that could potentially overwhelm the operating system, just sort of grind it to a halt. And whatever else this computer is doing would not function very well. So it would be nice if we could throttle back the number of worker threads that are running at any instant in time. All right, so the problem with trying to manage that right directly from the main program is we don't know, after we've done this pthread create, we don't really know how many workers we have running at any instant in time, right? Like when we ask a worker to do something, we create that thread, it goes off and executes, but the main program has no idea how long it's taking for one of those workers to finish. And it has no idea how many workers it has. So one idea might be, what if we were to place a limit? So what if we said int worker limit, and we said that was equal to 100. All right, so you can't have more than 100 workers. And then we could have an int worker count, and we'll start that equal to 0. All right. So now what we could do is, when we could have a loop here that says while worker count is less than 100, actually, while worker count is greater than or equal to 100, we'll just spin in a loop. Okay, so this while loop is just spinning round, and we're not allowed to actually create our next worker pthread until worker count drops below 100. All right, and then what we could do is, if we are allowed to pass pass that worker count, we could set worker count here, add 1 to that. And what we'll do is in the worker thread, when the worker is done executing, just before we exit, we'll delete from worker count. So, all right. So that reduces the worker count by 1. All right, so let's just look at what we have here and think about it for a moment. It seems like a plausible, at least a plausible first pass, right? Replacing a throttle on the number of workers. Oh, I said it's less than or equal to 100, but we could say worker limit instead. It's nice and generic. And if we pass, if the worker count is less than or less than worker limit, then we're allowed to slip past that while loop that acts as a guardian. And we'll increment worker count, and we'll be able to execute our code. Cool. So this seems like a reasonable strategy, at least at first blush. We now have a throttle, or at least an attempt at a throttle on the number of workers that are executing. But there's a couple of problems here. So one problem is, do we have a race condition potentially? So a race condition means we've got a situation with some data that's shared between concurrent threads of execution. So we have this main thread, and it's very interested in worker count. And not only does it read worker count, but it also writes to worker count. And we also have a worker thread, multiple worker threads, and those worker threads decrement from worker count. Now, the reason why this is a problem is this action, the decrementing from worker count, is not mutually exclusive. And there's a process that gets followed with adding to worker count and subtracting from worker count. That's a multi-step process. And the first thing that happens is the value of worker count gets read into a register. Then it gets changed, and it gets written back out to main memory. And because we have basically copies of worker count as we're processing, either adding or subtracting from worker count, we can end up with a situation where, well, I'll give you an example, where we would have something like this. Here's thread A. We'll do this. Thread A. I'll do it down here. I don't want to mess the code up here. So we might have this situation. We'll do it here. So we'll say this is the main thread. And then over here, we have a worker thread. All right. And the main thread it's going to read worker count. Well, let's say worker count is equal to 3. Okay. And the worker thread also says worker count knows that worker count is equal to 3. Okay. So at the same time, both the main thread and the worker thread would like to increment and decrement worker thread. So read worker count, register, into register A. And I have to move this over a little bit. Okay, worker thread has its own copy or has its own set of register values. So the worker thread is going to do something very similar. Read worker count. into register A. Add 1 to register A. Write register A to worker count. Worker count is 4. Okay? And now we allow the worker thread to run. Subtract 1 from register A. And write register A to worker count. And what's the value of worker count when this is all done? The value of worker count is 2. So what should have happened is the value of worker count when this was all done should be 3, because the main thread's adding 1 to worker count and the worker thread subtracting 1 for worker count. But because worker count is shared data between 2 concurrent threads, and they're both, that neither of them gets mutually exclusive access to worker count to mess with it, you can end up with this kind of situation. You could also end up with worker count being 3. You could also end up with worker count being 4 after the subtraction. So basically, you can have a lot of different and very unpredictable values for worker count. So we've got a problem here. So we could protect this by putting some mutual exclusion around worker count when it gets changed. So what we would want to do is when we change worker count, we're going to do a sem wait on worker count mutex. All right. And we're going to do a sem post on worker count mutex. And we're going to do the same thing up here when we're changing the value of worker count, sem wait on worker count mutex. Then sem post on worker count mutex. All right, and then we'll create a semaphore up here. It looks like there's a lot of extra code here that we really don't need, so I'm going to clean that up too. Whew, sure is a lot here. Okay. Get rid of all that. All right, so worker count mutex. So mutex is basically a semaphore with, it's just 0 or 1. All right, and then we're going to have to do a seminit down here. Oh, I got to close this comment too. All right, we'll do a seminit right up here. And I don't remember the syntax for this, so we'll look it up in just a second. But basically we want to initialize it to 1 so that someone can grab that worker count mutex to make the change. Okay. Cool. All right. All right. I think that's pretty good. Now, let's think about this a little bit more. Well, let's get that seminent correct first. Just want to make sure I get that seminent correct here. Okay, yeah, it's 0, 1. I think I have that correct then. All right, awesome. All right, so this is an adequate solution. We've got worker count protected, so we're not going to end up with any race conditions on worker count. However, we do still have one problem, and that is that while the main thread is waiting for workers to finish, it's competing here with the worker, right here, it's competing with the worker to get, competing for CPU with the worker while running this while loop. So this while loop here that's waiting for the count to get below worker limit is a busy wait. And that's an incredibly wasteful of CPU resources, because while we're just spinning our wheels here in the main thread, waiting for those worker threads to finish, we're actually competing with the worker threads for CPU, right? So it would be much better if we could have a blocking wait here in the main program for a worker to be finished. So it's possible to do that. And so what I'm going to do is I'm going to save this. I think what I'll do is I'll write this as busy wait. And then I'll write this as no busy wait. Okay. So what we should do instead is think about using a semaphore to help solve this problem. So we'll look at that next. So a strategy here would be to think about this worker count value here as a semaphore that we could wait on. All right, so maybe what we could do instead of having this worker count mutex is we could have a worker count semaphore. And we'll initialize this to worker limit. All right, so if we've got 100 workers that we'd like to have run simultaneously, then we'll set the worker count semaphore to worker limit. And then as we want to start a worker doing work, we're going to do a sem wait on worker count. So each time we do a sem wait on worker count, what will happen is that the worker count will be decremented by 1. So eventually, if we've got 100 workers working, the worker count will go to 0, and this while true for the main program will block. So we've got 100 worker threads running. We try to run our 101st worker thread, but we will block right here on this sem wait. Oops, I just noticed that this sem init, which I put inside the while true, that can't be there. That was an error in the other program as well. It needs to be out here. Okay, so we'll get rid of that. And I'm just noticing another improvement that we probably need to do here, which is we want to increment ID count. There we go. Okay, so now whenever we have a worker thread that runs, we're going to decrement the worker count semaphore, create our worker thread. When the worker count semaphore goes down to 0 and we do a sem wait, we're going to block. And now we have a way of synchronizing the main thread and preventing it from having more than 100 workers running at a time. Now the work we have to do up here in the worker thread is that instead of keeping track of this worker count, what we're going to do is do a sem post on worker count when we're done with the work that we need to do. So we'll do a sem post on worker count here. So the worker is going to do its work, and then it's going to sem post on the worker count semaphore. And when it does that, it will unblock the main thread that's doing a sem wait, assuming there's 100 workers that are running. It'll unblock the main thread so that the main thread can spawn another worker. So this is a really nice way of avoiding that busy wait. Remember, just moments ago, we had a busy wait that was doing a while check on a worker count variable. So there you go. We have a really nice solution to this worker dispatcher problem that doesn't involve busy waiting, that just involves using a semaphore, which is keeping count of the number of worker threads we have running at any instant in time. When you exceed 100, the sem wait here blocks the main thread and we don't have any more worker threads running.